Hello everyone, I hope that you're all doing well. My name is Richard and welcome to Group Advanced Concepts presentation number 4. So let's go over this week's topic. So in order to go from glycolysis to the citric acid cycle, we first must harvest pyruvates into acetyl-CoAs. This process involves many small steps which result in the main entrance in the citric acid cycle. So our goals for this week is to walk the audience through every step that is involved in generating acetyl-CoA from pyruvate. We must also focus on any cofactors needed and show how this process is reset at the end to allow for another pyruvate molecule to bind. So this slide shows the overall cellular respiration. And as you can see, it consists of 4 important steps: glycolysis, pyruvate oxidation, the Krebs or citric acid cycle, and the electron transportane / oxidative phosphorylation. And as you can see, for this week, we are mainly interested in step 2. Which is over here, pyruvate oxidation. So we're going to go from pyruvate, and we're going to form acetyl-CoA. So what is pyruvate oxidation? So first, it takes place in the mitochondrial matrix in eukaryotes and happens in the cytoplasm in prokaryotes. And it consists of 3 major steps listed here. So in the first step, a carboxyl group is removed from pyruvate, which is a 3-carbon molecule, as seen here, and it releases carbon dioxide. The 2-carbon molecule is left behind. This 2-carbon molecule in step 2 is oxidized. And if you recall from your chemistry class, oxidation is the loss of electrons. And these electrons are picked up by NAD+ to form NADH, as you can see here. And in the third step, the oxidized 2-carbon molecule, which as you can see in green here, is attached to coenzyme A, or CoA for short, to form acetyl-CoA. And just for background information, CoA is an organic molecule that is derived from vitamin B5. And the job of acetyl-CoA is to carry the acetyl group to the Krebs cycle. So where do these steps take place, pyruvate oxidation? So it all happens in the pyruvate dehydrogenase complex, PDC for short. And it consists of 3 distinct enzymes, abbreviated E1, E2, and E3. So E1 is the pyruvate dehydrogenase component, E2 is the dihydrolipoyl transacetylase, and E3 is the dihydrolipoyl dehydrogenase. There are 5 coenzymes that are required as well: thiamine pyrophosphate, TPP, lipoic acid, flavin adenine dinucleotide, FAD, coenzyme A, CoA, and nicotinamide adenine dinucleotide, NAD+. So this slide over here, you can see the structure of the thiamine pyrophosphate TPP. So you can see here. Here's lipoic acid. And this bottom step is the overall general step of the pyruvate oxidation. So that you can see the 3 steps here listed again: pyruvate, decarboxylation, then oxidation, and transfer to CoA to form the acetyl-CoA. So note that these steps must be coupled to preserve the free energy derived from the decarboxylation step to drive the formation of NADH and acetyl-CoA. So what does that mean? So let's break down each step. So step 1, decarboxylation. So this looks a little confusing, so let me break this down for you here. So first, pyruvate combines with the ionized form of TPP and is then decarboxylated to yield the hydroxyethyl TPP. So you're going to notice 2 separate reactions occurring. So you have your pyruvate, and let's start here. You have your TPP, and you're going to form the carbanion. So you have the negative group here, and the hydrogen here. As you can see here, it's lost, the electrons, it's lost here, and that's what this is. And you have your pyruvate, which is here. This reaction to form this hydroxyethyl TPP is where the decarboxylation occurs. So the pyruvate breaks down to acetaldehyde, which again breaks down to ethanol, which undergoes decarboxylation. and forms this group here at the end of the carbanion to form the hydroxyethyl TPP. So note that this step right here is the rate-limiting step in the synthesis of acetyl-CoA. And again, it's catalyzed by the pyruvate dehydrogenase component, or E1. And recall that the TPP is the coenzyme of the PDC. So now what do we do with that hydroxyethyl TPP? It has to undergo oxidation. So as you can see here, the hydroxyethyl group attached to the TPP is oxidized to form an acetyl group, while being simultaneously transferred to lipoamide, which is a derivative of lipoic acid. So as you can see over here, the disulfide group of the lipoamide, or lipoamide, which is this green structure over here, is reduced to its disulfhydryl form in this reaction, as you can see here. You go from two S's to this group right here. The reaction is also catalyzed by the PDC, or E1, and it yields this acetylipoamide over here. So in the third step, which is the formation of acetyl-CoA, the acetyl group is transferred from the acetylpoamide to CoA to form acetyl-CoA, as you can see over here. So again, the E2, or dihydrolipoyl transacetylase, catalyzes this reaction. The energy-rich thioester bond is preserved as the acetyl group is transferred to CoA, as you can see here. And acetyl-CoA, which is the fuel for the citric acid cycle, has now been generated from pyruvate. So just to break this down again, you have your coenzyme A here, and you have your acetylpoamide, and it's transferred. So as you can see here, the hydrogen group over here is placed over on the dihydrolipoamide, and the CoA group, or the acetyl group, gets attached to CoA. So this attaches to this, and this H attaches to this S, which is why we have these two molecules here. So the PDC cannot undergo another cycle until the dihydrolipoamide is oxidized to lipoamide. So what we need to do then is we need to regenerate the enzyme. So in order to do that, we need to have a fourth step. So in that fourth step, the oxidized form of lipoamide, which is here, which was generated earlier, right here, lipoamide. So this right here, this dihydrolipoamide, which was generated right over here, reacts with FAD to form lipoamide. And with that lipoamide, if you recall, we can undergo step 2 again. 2 electrons are also transferred to an FAD prosthetic group of the enzyme, and then to NAD+, which forms NADH. So in conclusion, remember that the pyruvate dehydrogenase complex, its purpose is to form 2 NADH and 2 acetyl-CoA. We also regenerated lipoic acid and FAD to continue pyruvate oxidation. And from this point, we can now move on to the Krebs cycle. Thank you very much.